Summarizing briefly, Newton's law of universal gravitation says if you have two particles m1 of masses m1 and m2 separated by distance r, gravitational force is g times m1 m2 over r squared, where g is some constant. And then we measure the constant in a lab, and we find that the constant has this value. We work out intuitively, if you double one of the masses, let's say you double m2, then m1 is pulling on the original m2 and the m2 that you add to double the mass, so it's going to give you twice as much force. And also m1 will be attracted to m2 with twice as much force, to the doubled mass with twice as much force, because the original mass is attracting it and the one you just added is attracting it. We can also see that the effect of doubling one mass on the force, just using the equation, here's the force of gravity if you have m1 and m2 separated by distance r. If you have mass m1 and 2m2 separated by distance r, this is the force. You divide this by this, you get 2. You get twice the force. Okay? If you double the separation, on the other hand, you've got to double r. So here's the original without doubling the separation. And here we double r, being careful to actually double r to square the thing, the r that we doubled. We don't write 2 times r squared, we write the quantity 2r squared. And this simplifies to this and then to this. You get 1/4 the force. And you can kind of think of this as the gravitational effect of m1 being spread over a sphere of radius r. Okay? Now, if you double r, you're spreading the effect of the same mass over a sphere of twice the radius, and the sphere is twice the radius, as we should understand, has 4 times the area, so that you're going to have 1/4 of the effect. So that's kind of an image that helps understand something about why this might be so, although it's not a rigorous explanation. Okay, well, the vector form of the law, we simply let vector F21 be the vector force exerted on mass 2 by mass 1, or particle 2 by particle 1. And we let R12 be a vector from F from the position of particle 1 to particle 2. Then, just adapting this, magnitude of F21 is your force of gravity, magnitude of R12 is your separation, so this becomes this. And then we just have to get a direction on this. To get a direction on a force of this magnitude, we use the R12 vector, which has this direction. We divide by the magnitude of the R12 vector, giving us a unit vector in the direction from M1 toward M2. And then, since the force F21 is in the direction back toward M1, it's going to be in the opposite direction of this R12 vector. So we put a negative sign out here, and now we have a vector form of the force. Now we look quickly at a big mass being orbited by a small mass, okay? Because anytime you have a small mass out here, as long as it isn't moving too fast, because it can be moving so fast that it has an escape velocity or exceeds escape velocity, and it never comes back. Okay, but as long as this mass is moving at a velocity that doesn't totally escape the gravitational field of this big mass, we're going to actually have an orbit. The attraction toward this mass is going to curve the path toward this mass, giving you an elliptical or circular, even circular orbit, circle being actually an ellipse. Okay, so we're going to make the assumption right now, because we actually want to develop the idea of a circular orbit, that V2 is moving in a direction perpendicular to the line between the two masses. Meaning, of course, then that the direction of V2 is perpendicular to the force attracting. Now, if the particle is moving in a direction perpendicular to the attractive force, then that force is going to do no work on it, so the velocity of the particle is not going to change. So we assume a very short delta t. then the delta S that we get from this velocity moving for that time is going to say pretty much perpendicular to F21. So the work done during that time interval is pretty much going to be 0. If the work done is 0, then the change in kinetic energy by the work energy theorem is going to be 0, so that the velocity won't change. So another way to look at it, of course, is just, okay, this force is not exerting any component in the direction of V2, at least at this instant. So V2 is not going to be changing at this instant. Now, I didn't state this real well, and I'm not real happy with it, but I'll say it anyway. Okay, so that F21 curves the path toward M1. Why does it curve the path? Well, by the impulse momentum theorem, in a short time interval, F21 is going to exert an impulse on V2, which is going to change the momentum of V2. What's the direction of that impulse? Well, if we multiply, if F21 is the net force, which is kind of our assumption here, then the net force times delta T is going to be our impulse, and that's going to be a vector. And that's going to equal the change in the momentum, and the momentum is a vector, mass times velocity, and the velocity is V2. Which means that we have a change in V2 that's equal to the F net delta T divided by the mass. And that's going to be in the direction of F net, isn't it? So if we multiply F net, checking, okay. If we multiply F net by delta T, we get a direction, a vector in the direction of F net, which means that we're going to get a delta V2 in the direction of F net. That's going to be this vector. Here's our original velocity vector. So our new velocity vector will be the sum of these, which is going to be turned in this direction toward the M1. Okay. Now, if we want to get a circular orbit, then the centripetal acceleration of the particle of mass m2 of the satellite, the centripetal acceleration is going to have to just be equal to the gravitational force. So they're going to be equal in magnitude. That follows that F21, the gravitational force, is then equal to m2 times the centripetal acceleration, v squared over r. Well, that means then that this expression is equal to this, and we can solve that for the velocity, and we find that the velocity is the square root of g times m1 divided by r.